take a little bit of a diversion from deep learning this morning, so I'm hoping you don't mind for a second. So I'd like to thank the organizers for inviting me and all of you for coming to hear my talk today. One of the things that we have found and that we see are that people ask questions about our software. So these are some examples of questions on, say, BioStars about a specific piece of software called Salmon, which we developed in our lab. And each one of these questions, at the end of the day, the answer ended up being, if you set a parameter to X, you'll get the result you want. You're setting the parameter incorrectly. And that's because all of the modern pieces of software that we have, such as Salmon, have a large number of tunable parameters, and it goes on and on and on. And if you set these parameters incorrectly, you're going to get results that aren't good, which means most people rely on the default parameter settings that come with an application. These were developed by the person who wrote the program. They're usually the ones that worked best to make themselves look good in a paper, but they're not always the best for every MBit because they're meant to be good on average, but the most interesting studies that we end up doing are rarely average. So here's an example of actually transcript assembly, which is the problem I'm going to be talking most about today, where the default parameter setting actually misses these two transcripts at the bottom. And I'm not showing it here, but there's clear evidence in the data that those transcripts exist, and they're both in the reference transcriptome. And this isn't just a problem inside bioinformatics and computational biology. This is actually a problem that we see sort of all over the place, whether you're doing integer linear programming using CPLEX or SAT solving. What parameters should you be using to come up with the best answer? So since we know all of these pieces of software are used and setting the parameters is a very important problem, and misconfigurations can actually give you false results, the question that we're trying to solve with this piece of work is, can we remove parameter choice as a source of error when we're doing, specifically here, transcript analysis? So I'm going to be concentrating today on the specific task of transcript assembly, in particular using a program called Scallop, which if any of you were at the RNA session yesterday, you saw Ming Fu talk about Scallop, so I'm not going to go into the details, but the main idea is you align reads to a reference genome, create a splice graph from there, and then decompose that splice graph into transcripts. Each one of these steps has parameters that, if you change them, change the decomposition, and at the end of the day, change the transcript assembly that you get. So what we'd really like to have is, given our aligned reads and our piece of software, we'd love to have some oracle that could look at the input and give us an answer and say, these are the parameter settings that you should be using. But oracles don't exist in real life, so we're left to do something a little bit better. And this is actually a problem that exists in machine learning and is sort of all over the place. This is sort of the hyperparameter tuning problem, and we can solve it using multi-arm bandit or something. But one of the issues that we have in transcript assembly is that even though Scallop is very fast is relative. So it's an hour and a half to run each iteration. So there's not really a way to, doing this in a serial manner for every input is not really going to work. So what we can use is something that I developed along with John Kazasioglu, who's in the audience today, called parameter advising. So parameter advising is a framework that basically takes the input that you give it and has embedded in it a set of parameter choice vectors. So each one of these parameter choices assigns a value to each of the tunable parameters in the scientific application that you're using. Using that set, we can have a collection of candidate outputs. These are candidate solutions to your problem that, using some sort of method, you can rank and select the best one. So in a way, a parameter advisor, when you use it, selects the best parameter choice by looking at the output. And just to sort of show that it works, we did this for multiple sequence alignment when I was doing my PhD, and we can see that you get an increase in accuracy. So here the vertical is the accuracy of the alignment chosen by parameter advising, and the horizontal is the size of the advisor set, which was on the last slide. And we can see as you increase the advisor set, you can increase the accuracy at the expense of having to use more resources. So parameter advising is embarrassingly parallelizable, meaning as long as you have enough resources, you don't actually lose wall time. with a small overhead for the estimator. So to apply this from multiple sequence alignment into transcript assembly, or into any domain actually, requires the two things that you have to do to reapply it. The first is coming up with the advisor set, which is just the collection of parameter choice vectors that you're going to use for parameter advising, and then coming up with an accuracy estimator. So transcript assembly is actually a little bit different because we have the reference. We know the reference, so we don't have to estimate accuracy. We can actually calculate the area under the ROC curve. After we get an assembly, we can get its actual accuracy. But the caveat here is that unlike parameter advising for multiple sequence alignment, we are not working with 5 parameter settings. We're working with in the 18 to 20 range. So when we came up with the advisor sets before, we exhaustively enumerated the parameter space, and that's just not a possibility for this new domain. So what we did discover along the way, though, in looking at which parameters should we use, is we discovered that each of the parameters is smooth when you look at it in isolation. So here's an example of 2 different parameters where we changed the parameter value while leaving the rest of the parameters the same on the default setting. And what we see is it's nice and smooth. There's a single global maxima, and there's no local maxima that are sort of off the beaten path. But we wanted to confirm that this wasn't just something in isolation when you look at one parameter, so we looked at pairs of parameters and we saw the same thing. Which means that we can do something like coordinate ascent, and it works well, even though it didn't work in parameter advising or in multiple sequence alignment. So we can do coordinate ascent. So this is an example of the trajectories of the coordinate ascent training on some examples. And you can see the area under the curve, which is the vertical axis here, as we go along with the number of iterations of coordinate ascent that you do, increases as you go along. And it increases quite a bit. But if you remember from 5 or 6 slides ago, I said it's too slow to actually do coordinate ascent. Why did I explain all of this? We can use coordinate ascent to pre-train the advisor set. And then at the end of the day, when we give it to the end user, when you rerun everything, you use parameter advising. So we're combining these 2 ideas, and we're using coordinate ascent as the pre-training, which you do once before you send it off to, say, a user in the lab. So that's exactly what we did. We used a set of 10 benchmarking transcript assemblies, or 10 RNA-seq experiments from ENCODE that are commonly used to benchmark transcript assemblers. And we used 3 different genomic aligners, which are also very commonly used. These are the outputs here, and I know this chart is hard to read and not really useful, but there's a couple things that you can point out here. One is that several parameters end up having, across all of the different experiments that we ran, they end up converging to basically the same parameter setting, which means our defaults, which the default here was 1, and they all basically converge to 11, which means our default was wrong, but it can still be a single default for that parameter. There's others that change across every example, which means these parameters need to be actually changed for each input. So we do actually need to do something here. So just to show the results of the coordinate ascent method, if we were to do this on every input, we could greatly increase the AUC. This is, again, those same 30 examples and the final AUC you get after doing coordinate ascent. So this raises AUC by 18%, which is great. But the question is, how well is it going to perform in parameter advising? So we did a leave one out experiment where we do parameter advising on the 18 examples that were from different experiments or different aligners that you didn't train on. So there's 30 examples, remove the 10 that use, say, HiSat, and the other 2 that used this first example, and that's the 18 that you're choosing from in parameter advising. And you can see even then we still get a very big increase in AUC, which is great. So then we went on to some testing data just to ensure that that this method's going to work. So we used 65 examples from ENCODE. So again, the training set was 10 experiments from ENCODE. We left those out. There's 65 more that are in the ENCODE database that are already aligned to the genome. So this represents sort of how it's going to work on average. And we show here the advising ratio on the vertical, which is just the AUC of the final transcript assembly chosen using parameter advising, and the horizontal is the default AUC. So one of the trends that's sort of obvious is that if the default AUC was very low, there's a lot of room for improvement, which means the advising ratio is high. But it's good that it actually worked that way. Otherwise, it wouldn't have been great. But we can see that the advising ratio is pretty high. In a lot of cases, we almost double, or in some cases, we almost double the AUC, which is great. So that sort of simulates how it's going to do on average, using different aligners, using different whatever. What if it was some sort of uniform experiment where you would run it through your own pipeline? So we took all of the RNA-seq experiments in SRA, did the same thing, and we see the same trend where if the default was low, then the increase in AUC is much bigger. But we do improve the AUC in almost every case. So there's one case here that's actually below this 1.0 line, which means that parameter advising decreased AUC, but that's because we left the default out of the training set for this experiment just to see what would happen. So the question is here, we said that you don't lose wall time if you have the resources to run everything in parallel. But not everybody has a 31 core machine sitting around that they can run this on. So what if we want to run it on our laptop where it only has 4 or 5 cores, 4 to 8 cores? So this is actually, there was a method that we developed again for multiple sequence alignment for finding advisor subsets. We called it Oracle set finding. But it basically, it's solving a problem that's very similar to facility location, and it becomes a little bit easier when your points are both the parameter setting and the example. So here, each point represents one of the examples of the 30 examples that we had in our training set. And between any 2 points is basically the difference in AUC that you get by excluding the parameter setting that was trained on my example. And if you set up that whole graph, you get a nice pretty picture, but then you can solve an ILP very quickly, and because this is only 30 parameter choices, this ILP solves without any problem. So what we did was we came up with sets of 2, 4, and 8, which are sort of the common number of cores that you might have in a machine. And the sets are here in this table, but what I'm showing here in the chart is the parameter choices that we had, so 31 things, and the frequency that they're used in the SRA training set. A couple features stand out, and one is that not all parameters are ever chosen, which is interesting in that. But the other thing is that even though the SRA data was all run through HiSat, many of the most frequently used, the most frequently highest AUC parameter choices were actually trained on Top Hat, which is a little surprising, and we're not quite sure why yet. So everything I've shown so far is actually using Scallop, but the question is, and Scallop was developed in our group, so the question is, does it actually work for other methods as well? So just to confirm that we weren't seeing some bias towards our tool, we did this on string tie as well. So using the same procedure I described all along, we trained 31 different parameter choice vectors for string tie, and we see that we still get a very high AUC improvement just by using parameter advising. And then to confirm that it's not just on the training, we did this again on the 65 examples from the ENCODE database, and we still see advising ratios above 1 consistently. So to summarize what I've talked about today, so I've shown that parameter advising can be applied to other domains. This is the first time it's been used outside of multiple sequence alignment. And one of the things that we encountered that we didn't really think about until we got into the meat of it is how do we come up with parameter settings in these new domains where it's not possible to just recreate the things that we did before. So we came up with a new way to find advisor sets that I think eventually will go into our corpus of as we go to new domains that we can move on to. So I know I'm running a little late, so there might not be time for everybody to ask a question that wants to. So if you have more questions than you have to ask today, feel free to find me in the poster session this evening. We also have a bioarchive link. And then finally, a plug for the rest of our group. I'd like to thank the whole group for helping with all of the talks and stuff. But there's 3 people that still have yet to talk from our group. So Guillaume are talking tonight, and Natalie is talking tomorrow, all in HitSeek and our funding agencies. So thanks.
Thank you very much. We do have some time for questions. Bill.
Hey, that was great. It's interesting stuff. I was thinking about applying it to other possible applications.
Yeah.
And one thing that occurs to me is maybe depending on the domain, you run the risk of overfitting, right? You're essentially doing grid search over a bunch of hyperparameters, and are you going to end up thinking that your error or your performance is better than it should be because you've used the same data to choose your hyperparameters that you end up evaluating on? Is that a problem in either of the settings you've looked at?
So we do, for this experiment, we do see a lot of overfitting. And there's some things that we would like to look into to sort of help with that. Because right now the coordinate ascent is performed on a single experiment, right? So you're really focusing on the one example and coming up with a parameter choice for that. So we might look into sort of averaging and doing coordinate ascent on a corpus and coming up with sets that way. But yes, there is definitely overfitting, and we're working to overcome that.
Other questions? If not, yep, Ollie.
Maybe a question beyond the immediate scope of your talk, but is there a way to apply similar approaches to settings where you do not have a clear supervision signal, or the supervision signal is fuzzy or partially lacking, which is in many cases also a key choice in genomic applications where you don't have that information?
Yeah, I mean, I think so. I think the question you're asking is if you don't have basically a parameter advisor or an accuracy estimator already. Yeah, so that's something we dealt with multiple sequence alignment, is we don't have a reference, so we had to come up with an accuracy estimator. So this problem is a little bit special because we didn't have to do that, so I left that part out of this talk. And but yes, in new domains, you do have to come up with a way to assess the problem, even if there's not a real way to answer that question. Yeah.
Thank you very much.
Thanks.
So let's thank Dan again.